Hello, Algebra 2 students. How's it going? I hope it's going well. We're on the very last unit activity, the Unit 10 unit activity. So go ahead and open up the activity and we'll go ahead and get started. Okay. So what we're going to be talking about mostly today is kind of the normal distribution and what we can say about confidence intervals and things of that nature. So to start, I want to kind of go over this thing. This is basically a normal distribution bell curve. Now, when you look at this, there's a few things to note. This thing right here in the middle, on the bottom, hold on. Okay, so this thing right here on the bottom, this symbol mu, this is the Greek letter mu, and in this instance, it represents the mean or the average of the population. So that's what mu represents. And then the other symbol you'll see that you may not be used to is this one right here. And this one's sigma. And this represents the standard deviation of the population. So what is this chart trying to show? Well, this is trying to show that for a normal distribution, half the values will be above the mean. So 50% of the values are above the mean and 50% of the values are below the mean. That's why this is symmetric like this. So it's the same on both sides from the mean. What it also shows is that you notice these numbers on top, 68%, 95%, 99.7%. What it's showing is that 68% of the values will fall within one standard deviation of the mean. So you can see most of the values are within one standard deviation of the mean. 68% of the values are within one standard deviation of the mean. 34% in this section and 34% in this section. Okay, so together 68% of the values are within one standard deviation of the mean. And 95% of values will fall within two standard deviations of the mean. And 99.7% of values will fall within three standard deviations of the mean. So this is going to make more sense as we go on. But basically what I want you to see here is kind of know these numbers, 68, 95, 99.7. And that the values are most likely going to be close to the mean. And this is for a normal distribution. So that's key too. This is for a normal distribution. Okay, so let's go ahead and match these tiles here. It says 95% of the data. So for 95% of the data in a normal distribution falls within two standard deviations of the mean. So from here to here, in other words, from below two standard deviations to above this gap, 95% of the values will be within this section of the curve. Okay, so that's what it means, within two standard deviations of the mean. And based on what I just explained, see if you can put in these other two in the correct spots and drag them to the correct spots here, okay? Okay. So one of the things we're going to talk about here is statistical significance. Now, what does that mean? Well, if you were to grab two random samples from a population, so you grab a sample and another sample from a population, those samples will have different means and different standard deviations, even though they came from the same population. But that's going to happen even with random chance. If you take from the same population and two random samples, you know that the means are probably going to be different by at least a little bit. And the standard deviations will be different by at least a little bit too. But are they statistically significantly different? That's what we kind of are going to go over right now, because you know they're going to be different, but is it within a reasonable range of difference? Or are they so different that it's significant statistically speaking? And that's what it's talking about, statistical significance. Okay, and we're going to talk about that deeply in this activity. Okay. Let's talk a little bit what a sample means. So if you have a population like this, a sample is just a group from that population. Now the sample should be a random group from the population. So the sample should be randomly selected from the population. That's key also. And that the sample should represent the population in a good way. Yeah, so that's what a sample is. And the bigger the sample, the more you can predict better about the population. A bigger sample is always better. Now, there are some populations that are so big that you can't possibly ask everyone in the population about a thing, right? Let's say you want to figure out what are people's favorite color in the United States. Now, could you ask everyone in the United States? Probably not, right? That's too many people. It'd take too long, and it's just unreasonable to try to conduct a study with everybody in that big of a population. So what you might want to do is a sample. So you might instead say, well, I'm going to ask 1,000 people, or maybe 2,000 people their favorite color. The bigger the sample that you take, the better your data is. You can imagine out of everyone in the US, you won't be able to ask everyone, but if you only ask 2 people, well, that's not very useful information. If you ask 2,000 people, well, then you'd be able to say more about the population. The bigger the sample is always better. Kind of the lesson here. Okay. This has to do with experimentation. Basically, when you take a sample, a lot of times your sample will be split into 2 groups. You'll have a treatment group and a control group. That goes with any experiment. So you probably learned this in science class. Then when you're doing an experiment, you'll have the treatment group and a control group. And then you're comparing those. And you're seeing if there's a statistical significance between those 2 groups. Okay. Let's go ahead and move on to page 9 in the activity. All right, I'm going to go ahead and read this, and I want you to follow along as I read aloud. Suppose you have 10 green bell peppers of various sizes that have been part of an experimental study. The study involves treating the peppers with a nutrient supplement that would produce larger and heavier peppers. To test the supplement, only 5 out of 10 peppers were treated with the supplement. All 10 peppers were of the same variety and grown under similar conditions, other than the treatment applied to the 5 of the peppers. Okay, so you have 10 peppers, 5 are the treatment group, 5 are the control group. So the ones that are the treatment group receive the growth supplement. Okay, your task is to examine the claim that the nutrient supplement yields larger peppers. You will base your conclusions on the weight data of the peppers. The table shows the weights of 10 peppers in ounces. Note, do not be concerned with which peppers receive the treatment for right now. In this task, you'll divide the data into 2 portions several times. Take their means and find the differences of the means. This will create a set of differences of means that you can analyze to see if the treatment was successful. All right, so we can see peppers numbered 1 through 10 here, and you could see the weights of the peppers. So pepper 1 weighed 8.2 ounces and so on. Okay. A random number generator assigned each pepper to one of 2 groups. The weights of the peppers in each group, given 3 randomizations, appear in the table. So they split into group A and group B. 5 peppers in group A, 5 peppers in group B, and they're just random, right? So randomly, 5 of these got put into group A, and then in 5 of them, the other 5 into group B. Then they randomly selected again, basically starting over into 2 groups again, and a third time. So what they're basically taking, splitting these into random groups, and they did it 3 times. For each table, calculate the mean weight for each group, X bar A and X bar B, and find the difference of the mean of group A and the mean of group B. So the difference, that means we're going to subtract them. Okay, so after the first randomization, so you see it has X with a bar over it and A. That means that's the mean, okay? Now I know I talked about the mean being this symbol mu. Well, this is the mean of the population. But if you want a mean of a sample, this is X bar. So whenever you see X with a bar on top, X bar, that is the mean of the sample, whereas the mu is the mean of the population. So we're going to be calculating X bars in this case. We're going to be calculating the means of these samples. So first, let's look at group A. So how do we calculate the mean here? Well, we want to add up these numbers here and divide by how many there are. So in this case, there are 5 numbers. So we're going to add up these 5 numbers in group A and divide by 5. That's how you calculate the mean of a sample. You just add those sample values together and divide by how many there are. In this case, divide by 5. So let's go ahead and do that. So I've got 13.6 plus 12.1. And by the way, you should be doing this on your own as well. 15.9 plus 11.2 plus 9.7. Okay, so I add them together. I got 62.5. Then I divide by 5. And I've got 12.5. So for my first randomization, my X bar for the A's is 12.5. Let's do the same for the group B in this first randomization. So let's go and add those together. 9.2 plus 8.2 plus 11.5 plus 13.8 plus 14.6. Okay, got 57.3. Again, I want to find the mean, so I divide by how many there are. In this case, dividing by 5, 11.46. Okay. And lastly, we want to find the difference between them. So we're going to go and subtract these two values, X bar A minus X bar B. So we're subtracting these two sample means. 12.5 minus 11.46, 1.04. That's how that's done. So I want you to do the same thing for the second randomization and for the third randomization. So do the same thing we just did for the first randomization. Do that same thing. So calculate the sample here, the sample mean here, sample mean here, and subtract. And do that for all 3 of these groupings. Okay. So you might want to pause the video and go ahead and do that for each of these. When you're done, resume the video, and I'm going to move on to the next question here. Okay, part B. What does the difference of means of each group indicate? What makes the mean of one group greater or less than the mean of other group? Okay. So the difference in means of each group, basically, the higher the difference in means, that means the average of this group is bigger than the average of that group by this much. So if you were to take a random one from group A and a random one from group B, they will be different from each other on an average of 1.04. Okay, so if one group has a higher mean than another group, then we know that the group with the larger mean had larger numbers in its sample. On average. The difference between the means indicates that there's a difference between the samples. Basically, there will always be a difference between the samples, even if the samples were taken from the same population, because the two samples will not be identical. A mean difference of 0 between the two groups, well, that just indicates that these two samples have the same mean. They have the same average. So on average, the values are the same. And also that there's no real significant difference between the two groups. So I want you to explain that there. I explained it in words, but you should write it down in a complete sentence here in your own words, please. Let's move along. Okay. When we take a bunch of those samples that we took and re-randomize a bunch of times, the difference between the means will approach a normal distribution. And we'll talk more about this, but basically that's that. Okay, let's move on. Okay. Okay. Fitness experts advise people who want to lose weight to drink protein shakes after workout sessions because it helps build muscle mass and speeds up the weight loss process. To test the effectiveness of protein shakes in losing weight, 200 adults between the ages of 25 and 40 years were divided equally into two groups, a treatment group and a control group. The treatment group was asked to drink a protein shake after every workout session for a period of 6 months. The subjects' weights were noted before and after the treatment. So the treatment group gets protein shakes after the workouts, okay? Okay, the control group does not get protein shakes. All right, now the results showed that the mean change in the amount of weight loss by the treatment group is 8 points more than the control group. To test whether the results could be explained by random chance, researchers created a table that summarizes the results of 1,000 re-randomizations of the data with differences of means rounded to the nearest 2 points. Consider the significance level to be set at 5%. So results less than 5% can be considered statistically significant. So what does that mean? Again, statistically significant means that it's unlikely to occur with random chance. In this case, we're doing a 5% significance level, meaning that if results are less than 5%, that means that given random chance, those sorts of results would be less than 5% chance to happen. Okay. Okay. Determine the probability of the treatment group's mean being greater than the control group's mean by 8 points or more. Okay. So if we look at these, the treatment group minus the control group, so that's what we got here. So when you see, for example, 0, that means that there were, if you look at the treatment group and you subtract the control group's means, it happened where there was no difference between them 0 times. Or where there was no difference between them, that happened 201 times. Basically, when these two numbers are the same, that gives you a 0. That happened 201 times. Okay? Because there's 1,000 re-randomizations. Basically, this is what you would expect with random chance. With random chance, this is what you would expect. Basically, if there was no difference between the two groups, the treatment group and the control group, if there was no difference, here's the data you would expect. You'd expect that there was 0 weight loss difference. That has the highest number here, right? You'd expect 12 pounds of weight loss difference 1 time out of 1,000, or 2 times out of 1,000 the other way. This is random, right? These were randomly basically tallied. So it's not quite symmetrical, but it follows pretty closely to a normal distribution. We're very few on the edges over here and over here. Okay, determine the probability of the treatment groups being greater than the control groups by a mean of 8 points or more. So treatment group greater than control, that would be positive 8, 10, or 12. So that's 8 or more. That's these 3 rows here. So how many times did that happen? Well, that happened, and I'm going to go use the equation editor here. That happened, and we're going to write as a fraction. It happened 8 pounds difference. That happened 26 times in the randomizations, plus 10 pounds difference. That happened 8 times, plus 12 pounds difference. That happened 2 times out of 1,000 different re-randomizations. As a decimal, which usually a lot of times we want our decimals as a our probabilities as a decimal. So 26 plus 8 plus 2, 36 divided by 1,000. 0.036. So as a percentage, that's 3.6%. Okay. Now remember, we wanted, if its results are 5% or lower, then we consider it statistically significant. So we would consider this statistically significant. So are the results statistically significant? We want to say, yes, these results are statistically significant because 3.6% is less than the 5% significance level. Okay, and I want you to explain that in your own words. So we would say 3.6% is statistically significant because it is less than the significance level of 5% that we set earlier. So what does it mean in the context of drinking protein shakes, weight loss? So since there's a statistically significant difference, we would say that since these is a statistically significant difference, that means that the data suggests that drinking protein shakes does have a positive impact on weight loss. Okay, so I want you to explain that there. Make sure you're using the term statistically significant in your answer. Question 2. According to a research study, people are able to better manage their time when they wear watches than when they use mobile phones or other gadgets to keep track of time. To test this, 300 college students were randomized into a treatment group and a control group. The treatment group was asked to wear a watch every day, and the control group was asked to avoid wearing a watch for 50 days. The number of occasions when students from both groups arrived later than their scheduled time was noted. The results of the experiment showed that the mean score of the treatment group was exactly 15 points less than the mean score of the control group. To test whether the results could be explained by random chance, the researchers created the following table, summarized the results from 1,000 randomizations of the data with different means rounded to the nearest 5 points. Consider the significance level to be set at 5%, so results lower than 5% can be considered statistically significant. Okay, so this is the random re-randomizations. So this is what you'd expect if there was no difference. Determine the probability of the treatment group's mean being lower than the control group's mean by 15 points or more. The treatment group being lower, meaning those are the negative ones. When the treatment group is lower, then when you subtract them, that gives you a negative. So we're going to do 15 minutes or more, right? So 15, the negative 15, the negative 20, and the negative 25. So the number in those groups were 50, 18, and 10. $1,000. We add those together. So 0.078, meaning about 78 or 7.8%. Okay. Is this statistically significant? So 7.8%, is that going to be statistically significant? Well, remember, we set our significance level to 5%. So if it's lower than 5%, we would say it's statistically significant. Well, this is higher than 5%. This is 7.8. So we would say it's not statistically significant. So see if you can explain part B and see if you can answer part C. So when they're not statistically significant, what does that tell you? See if you can answer those. Okay, let's move on, move on, move on. Okay. So here we're going to talk about basically two different boxes for this product, Elbow-Roni. They want to determine if the red box or the blue box sells better, if there's a statistically significant difference between these two boxes. What are the mean values of the people who would purchase the red box and the blue box, respectively? Use the spreadsheet's average function. So right here in this paragraph, let's go ahead and read it. It says, as a member of the marketing team for a pasta manufacturer, you want to find out whether there's any difference in the mean number of people who would buy the new macaroni product, Elbow-Roni, if it had a red box and if it had a blue box. In each session, you bring in 30 people to try Elbow-Roni and have them respond to whether they would buy this product over the competitor's product. Suppose you conducted 45 sessions with the red box and 60 sessions with the blue box. This data sheet gives you the number of yes responses to the survey for each session. Note that the two samples are of different sizes. Okay, so go ahead and click on this data sheet, and it should download a Excel spreadsheet like this. Make sure you go to the top here and click Enable Editing, because we're going to need to edit some stuff. And you can look down here. So it shows you the session number with the red box and the number of people who would buy it. So in session 1 for the red box, 13 of the 30 individuals said they would buy it. And then with the blue box in the first session, 15 people said they would buy the blue box. Okay, and then you could see these numbers as you continue down. Notice that for the red box, the sample, the number of sessions was only 45 sessions, whereas for the blue box, there was 60 sessions. Okay, see session 45, session 60 there for the blue box. Now we want to calculate the mean for both the red box and the blue box. So how do we do that? Well, when you're in Excel, there's actually a very fast way you could do this. So what you would do is you would highlight everything down here, all the way up to this. So I want to highlight all of this column, but not up here. So just the numbers here, the number of people who would purchase. So go ahead and highlight that, all these numbers here. And then you want to go to, if you go to formulas on the top toolbar, go to formulas. Over here on the left, you'll see auto sum. If you click on that drop-down menu, you can go to average. And what it does is it automatically computes the average. So you can see the average for the red box, there was 15.111 repeating average there. So we're going to call it 15.11. 15.11 is the average number of people that said they would buy the elbow roni with the red box. Let's go ahead and do the same for the blue box. So I'm going to go highlight this column and go to AutoSum, average, and it spits out the average right down here. So here, 16.85. So we know there's a difference in mean, right? We can see there's a difference in the mean, the average number of people. That's normal. We expect that. But is it a statistically significant difference? That's what we need to find out. So what are the mean values of the people who had purchased the red box, the blue box, respectively? So go ahead and answer that. So for the red box, the average was 15.11. For the blue box, it was 16.85. So go ahead and answer those in complete sentences there. The difference between the sample means, so you'd subtract those sample means, 16.85 minus 15.11, and whatever you get there, then you're going to put that there. Okay. Moving on. You should have gotten a sample difference of 1.74 when you subtract those two means, by the way. Now we're going to use this formula right here. So you might want to write this one down. This is to find the standard deviation of the difference of the sample means by using this formula. So I'm going to go ahead and write that down. And you should probably write that down too. So sigma sub 1 squared divided by n sub 1 plus sigma sub 2 squared divided by n sub 2. Okay. The n's, by the way, are the sample sizes of the two groups. Okay. And the sigmas are the standard deviations, right? We talked about sigma being standard deviation before. So now, there's also a piece of information we want right over here, and it says the standard deviations for the red box. So for the red box, it was 3.868. So that's sigma sub 1. So sigma sub 1 is 3.868. And sigma sub 2 is 2.933. So you see how there's sigma sub 1 and sigma sub 2? And they go in the formula here on the top of these fractions. That's what these two numbers are. Okay, so that's our sigma sub 1 and our sigma sub 2. I'm going to go ahead and write those numbers to the side so I have them later. And they're going to be important to when we are calculating this formula. Okay. Okay. What is the sample size for each population? So the sample size for the red box, well, that was the number. If we go back here, the sample size for the red box, well, that was 45, right? Because there was 45 different sessions. Okay. So the sample size for the red box was 45. Okay. Now, I want you to also write what the sample size for the blue box is, okay? And that should be 60. Use the standard deviation values of the two populations to find the standard deviation of the sample mean differences. Round your answer to 2 places. So here's where we're going to be using that formula that we had before. Okay. I like to use the equation editor. That's when you click on this little tool right here, and it'll bring up this equation editor. And we're going to be using that formula that we have before. So hopefully you wrote it down. But let's see here. Okay, so there was like two fractions in here like this, right? And remember, it was sigma sub 1 squared, right? So sigma sub 1 was 3.868, and that value is going to be squared. So right here, you could do a superscript like that and make a squared like that over the sample size from that group. So the sample size from the red box was 45. Similarly, for the blue box, it was 2.933 was the sample standard deviation. That gets squared from the formula. Over the sample size there was 60. Let's go ahead and start this calculation here. So it's going to be the square root, and I'm going to go ahead and put this in the calculator. So 3.868 squared divided by 45. Okay, that gave me 0.33, and I'll probably go to 4 decimal places here. So 0.3325 if I round to the nearest fourth decimal. So I did this number here, squared, and then divide by 45. Let's do the same right here. So 2.933 squared divided by 60. 14.34. Make sure you're rounding correctly there as well. Let's go ahead and add those together. That's 0.4759. And lastly, let's take the square root of that. And that gives us, if we're rounding, now we'll just round to 2 decimal places. So that's what I wanted in the answer. Round your answer to 2 decimal places. So 0.69 in this case. I know that the question only asks for 2 decimal places. So why did I want 4 decimal places throughout all the steps? Well, if you use more decimal places throughout your steps, it'll help reduce rounding error when you get to the end, even when you don't want that many in the end. Hope that makes sense. Okay, so that was using that formula. So 0.69. Okay, you calculated a standard deviation of the sample means differences to be 0.69. You also calculated the sample mean difference to be 1.74. Now you'll determine whether the difference is significant for the purpose of constructing a confidence interval. Assume that there's no difference between the population means. What is the 95% confidence interval for the difference of sample means? Okay, so for a 95% confidence interval, they're using the number 2. So why are they using the number 2 for a sample for a 95% confidence interval? Well, because for 95% confidence, that's 2 standard deviations away. So our confidence interval is basically asking if there was no difference between the 2 boxes, then we would be 95% confident that they would be a certain distance from each other. The 2 sample means would be different from each other by only a certain amount. So how much would that be? So if there was no difference, so we would say there was 0 difference in the population, plus or minus 2 times and it would be 0.69. Okay, because remember, this is a standard deviation. So 2 standard deviations above or below. That's why there's plus or minus there. So that's plus or minus 1.38. Okay, so if there was no difference between them, we would be 95% certain that it would fall between those two numbers. The difference would be between negative 1.38 to positive 1.38. So this is a 95% confidence interval. In other words, we could, if there was no difference between them, we could be 95% certain that the difference in the average means will be this far apart. Okay. Hold on, I'm gonna go grab a charter. Okay. So this is your 95% confidence interval. That's what we're going to put here. Now our sample mean was 1.74. So our sample mean was 1.74. The sample mean differences. So what does that mean? So what we would say is that this mean is outside of this interval. 1.74 is above 1.38, so it's outside this interval, which means that this sample mean is outside the 95% confidence interval. So, in other words, this sample mean is statistically significant at a 95% confidence interval. So, is the sample mean difference within the confidence interval? We would say, no, it is not. 1.74 is not within that confidence interval. So we would say that the difference of the sample means is statistically significant, meaning that it is statistically significant. A statistically significant amount of people prefer the blue box, right? This mean is statistically significantly bigger than this mean. So what can we conclude? Well, based on that, which color box should they go with, or does it not matter? So try to answer that question there. I hope you'll be able to get that. And that's that. Okay, I hope that lesson all made sense. If it didn't make sense and you still have questions, you can feel free to email me anytime. And my email is ttrigg at ofy.org. So that's ttrig at ofy.org. Okay, and I hope that made sense, and good luck.